Hello, students. Let's start with a simple thought. Why does sugar dissolve in water so easily, but only up to a certain limit? That very everyday observation leads us into the fascinating concept of saturated solutions. A solution is simply a uniform mixture of solute and solvent, for example, salt and water. But what really happens when you keep adding solute? Initially, the solvent particles surround and separate solute particles, making the mixture look perfectly clear. But soon, a stage comes when no more solute can dissolve. This is the idea of saturation. Keep in mind, this process is controlled by temperature, nature of solute, and solvent interactions. As you watch the slide, think of your cup of tea. Why do sugar crystals sometimes settle at the bottom even after stirring? That's saturation in action. Now, let's define solubility more precisely. The solubility of a solute in a solvent is the maximum mass of solute that can dissolve in 100 grams of the solvent at a given temperature. Formula: solubility equals the weight of solute divided by the weight of solvent multiplied by 100. For example, if 36 grams of sodium chloride dissolves in 100 grams of water at 25 degrees Celsius, then we say the solubility of sodium chloride at that temperature is 36. We can even calculate it mathematically using the formula solubility equals the weight of solute divided by the weight of solvent multiplied by 100. That's solubility equals open bracket weight of solute divided by weight of solvent close bracket multiplied by 100. And remember, temperature must always be specified because it directly affects how much solute can dissolve. So, what controls solubility? First comes temperature. For most solid solutes like potassium nitrate or sugar, solubility increases when temperature rises. But gases behave differently. They become less soluble when temperature goes up. That's why your cold soda fizzes less when it warms up, because carbon dioxide escapes more easily. Next comes the nature of the solute and the solvent. There's a famous chemistry saying, like dissolves like. Polar solutes like common salt dissolve in polar solvents like water, whereas nonpolar substances like oil dissolve in nonpolar solvents like benzene. Pressure hardly affects solids and liquids, but it has a big effect on gases. Think of soda bottles again. Carbon dioxide gas is forced into water under high pressure, and when the cap is opened, the pressure drops and the gas escapes. Finally, there is the concept of saturation. Beyond a certain point, no matter how much solute you add, the solution refuses to dissolve more. That is when a saturated solution is formed. Now, how do chemists actually determine solubility in the laboratory? Let's take potassium chloride in distilled water as an example. We begin by adding small amounts of potassium chloride crystals into water at a fixed temperature while stirring continuously. At first, the crystals disappear, but gradually you'll see some undissolved salt settling down at the bottom. This means the solution has reached its saturation point. We then filter or decant the mixture to separate the excess solid and collect the saturated solution. This clear solution contains exactly the maximum amount of solute that can dissolve in the solvent at that temperature. On your screen, you can see the laboratory setup with a boiling tube placed in a water bath to maintain constant temperature and the solute being stirred into the solvent. Once we have the saturated solution, the next step is to calculate solubility. The procedure goes like this. First, we take a clean, dry evaporating dish and note its weight. Let's call it capital M. Then we add a known amount of the saturated solution and weigh again. This new weight is capital M1. We then heat the solution gently to evaporate the solvent, leaving behind only the solute residue. Now we weigh the dish again. This is capital M2. From these three weights, we calculate Weight of solute equals m2 minus m. Weight of solution equals m1 minus m. And the weight of solvent is simply the difference between the two, solution minus solute. Finally, we put it into the formula solubility equals open bracket m2 minus m close bracket divided by open bracket m1 minus m2 close bracket multiplied by 100 at that particular temperature. Let's work through a numerical example to make it clearer. Suppose the weight of the empty dish, m, is 20 grams. When we place it with the solution, the weight m1 is 50 grams. After evaporation, the dish with solute weighs 30 grams, that is m2. So, the weight of solute is 30 minus 20, which is 10 grams. The weight of the solution is 50 minus 20, which is 30 grams. Hence, the weight of the solvent is 30 minus 10, which equals 20 grams. Now, solubility equals 10 divided by 20 multiplied by 100, which gives us 50 grams per 100 grams of solvent at the given temperature. Isn't that a neat and practical way to connect laboratory work to real numbers? So to sum up, solubility is the ability of a solute to dissolve in a solvent at a specified temperature, usually expressed as grams of solute per 100 grams of solvent. It depends on several factors like temperature, the nature of solute and solvent, and pressure in the case of gases. We also saw how to experimentally determine solubility using a saturated solution, evaporation, and a simple formula. And finally, we solved a numerical to see how the calculation works in practice. The concept of solubility is not just a textbook idea, it explains why your soft drink loses fizz, why salts crystallize in lakes, and why pharmaceutical companies carefully choose solvents for medicines. I hope today's session has helped you see how deeply chemistry connects with everyday life. Until next time, keep exploring, keep asking why, and you'll find chemistry hidden in every sip, every spark, and every solution.